Hi, my name is Jad Zaytoun. My student number is 215-909-476, and this is my answer to question 2 of assignment 1.
So I started this off by assuming that T1 is greater than T2. That way the torque produced at pulley B is opposite to the torque produced at pulley C. And there we get that since we're given that the tighter side was 30% more force than the loose side of this belt system, I got that T2 is equal to 0.7 T1. Also assume that the body is in equilibrium. Here I calculated the torque of the pulley system at C, which turned out being 4.8 kilonewtons times meter. And here I calculated the torque at pulley B, which was, and then substituted T2 as 0.7 T1. And there I get that TB is equal to 0.3 T1 times 0.5 meters, which is the radius. And here I calculated, since I assumed that the torque must be equal and opposite for the body to be in equilibrium, I got that 0 is equal to TB minus TC. So I just plugged in all my variables and I got that T1 is equal to 32 kilonewtons and that T2 is equal to 22.4 kilonewtons, which is just written right there. For part B and C, I kind of did them together. I started off by writing a singularity function, which was Q of X is equal to, I also assumed that R1 and R2, the reaction forces at the pins on each end, were going up and were positive forces. So I started out with Qx is equal to R1 x to the negative 1 plus 55.4 x, which is just the addition of the two forces we found on the previous page. 55.4 x minus the distance to the negative 1 minus the force at the second pulley, x minus the distance to the second pulley to the negative 1 plus R2, which is our second reaction force. And then I just integrated to get v of x and m of x using the singularity function rules. So for the first one, for v of x, it's basically the exact same thing, just everything to the 0 now since they're all point loads. And then m of x was the same thing, now just everything to the power of 1 since everything is just a point load, so they all follow the same rules. So my first step was setting v of x equal to 0 at x is equal to 1.041 meters, which is this end of reaction 2. And that I get this equation, which I labeled as number 1, which is 0 is equal to R1 at 1 meter, or R1 times 1 plus 55.4 times 1 minus 8.8 times 1 plus R2 times 1. And then to solve for R2, to solve for R2 at m of x is equal to 0. So the moment is equal to 0 at x is equal to 0. So yeah, at the origin, the moment is equal to 0. So then I plug that in. So 0 is equal to 55.4 times the distance minus 8.8 times the distance plus R2 times its distance as well. And since x is 0, then that could just, everything was just the distance from the origin. And the first reaction force was taken out since it is R1 times x, which is just 0. And there I get my second reaction force is negative 12.6 kilonewtons. So there I found that my initial assumption was wrong and it's actually aiming down. And then just plugging all that into equation 1, I got that R1 is equal to negative 34 kilonewtons. So the same thing, my initial assumption was wrong and the force is now aiming down. Using those same singularity functions, I just kind of turned them on and turned them off to get a v of x graph. Looks like this. It starts at negative 34 kilonewtons. Once it experiences the 55.4 kilonewton force, it goes up to 21.4. And once it experiences the 8.8 kilonewton, goes down to 12.6 until the end, and then the negative 12.6 kilonewton force brings it down to 0. And here in my moment graph, it starts off at 0, goes down to 11.8 kilonewtons, which is just the initial force times the distance of 0.34 0.347 meters, so it's 11.8 kilonewtons times meters. And then just turning stuff on and off in the singularity function, find that the second point of interest, which is at point C, which is the 8.8 kilonewton force, is 4.37 kilonewtons per meter, and then reaches 0 as the last part of the singularity function is turned on, which is the 8.8 kilonewton. And that is part B and C altogether. Part D asks for the maximum bending moment and where it's located, and determining the bending stress and the torsional shear stress at that location of maximum bending. And here I saw that the max bending moment would be at pulley B, since we saw it here in our moment diagram, that it's right at pulley B. And I start off by finding my second moment of area and my polar moment of inertia, and then plug that into my moment equation, just using the moment I got from here, and then my torsional shear equation, which is just the torque pulley B plus the times the radius divided by the polar moment of inertia, and there I get that the maximum bending stress is 69.55 megapascals, and the maximum torsional shear stress is 14.51 megapascals. And finally, for part E, it was asking to find the principal stresses and the maximum shear stress. So I start off by drawing the little body, which would be at the bottom of pulley B at the negative y area. So then these are my maximum bending stresses in the x direction, and these are my maximum torsional shear stresses going clockwise in the x and then counterclockwise in the y. Started by drawing a Mohr circle with my first point, which is the x, which is 69.55 megapascals in the x direction, then 14.51 torsional shear, and then 0, and then negative 14.51 torsional shear. And then just found the radius here, which would turn out being my T max, which would be the plus and minus moments. And then my sigma 1, which is the distance from the center to the edge of the circle, or the center plus the radius, which gives me 72.46 megapascals. And then my third principal stress, which would be the center minus the radius, which is sigma 3, and then my sigma 2, which is just 0, since this is just a two-plane stress. The plane stresses therefore are sigma 1 is 72.46 megapascals, sigma 2 is 0 megapascals, sigma 3 is negative 2.905 megapascals, and the max shear stress is plus minus 37.68 megapascals.
And that is my solution. Thank you.